Hello there. In this video, I'll be explaining to you how numbers in GBG actually work and how we can use that information to make a signal that can turn off any input. You can see here we have an input constant here that says 1, and when I press this button, it turns into 0. And note that this doesn't just send a negative 1 to it. See that if I change this to any number, like for example 48, when I turn this on, it's able to turn this number off. So at the very end of the video, I'll go over how this is made and how it works. But to reach to that point, we first need to understand how numbers actually work in GBG. So numbers in computers are stored as data. And since they are stored as data, there is basically a limit of how big a number can be. In a lot of systems, numbers are stored in such a way that can allow up to 4 billion possible numbers. So GBG is one of those systems. In GBG, there are a total of around 4 billion possible numbers that can be represented inside the game. Now, in more primitive systems, if you have, say, 4 billion possible numbers, the way that a number is represented is basically just the raw number. Like, for example, if you have 4 billion numbers, then you can represent numbers 0 up to 4 billion. So that's all 4 billion numbers that you can represent in that system. However, GBG uses something called floating point, which is widely used among basically every computer in existence right now. And it does something really clever to make the most out of those 4 billion numbers that are available to us. So as I mentioned earlier, if there's 4 billion numbers, if you do it like the most simplest way possible, that only allows you the numbers 0 to 4 billion. So for example, that allows you to represent numbers like 1,234,567,000, etc., etc. But that also means you can't represent any number bigger than this. So you can't represent, say, 1 trillion or 1 quadrillion. And that also means you can't represent decimal numbers. So like 0.1, 0.0001. It can't handle any of those because you already spent all 4 billion numbers on the numbers from 0 to 4 billion. So what did the old programmers do to make the most out of these 4 billion numbers to represent way more meaningful numbers that we might want to use? What they did is, for each number, they split it into 2. So instead of having, what is it? This is a 10-digit number. Instead of having one 10-digit number, they split it into 2 numbers, one 7-digit front number, and then another 2-digit number to represent the number of zeros to append to the back. Let me explain what I mean by this. So the 7 front digits are self-explanatory. The number can represent, like, say, 1,234,567. But since it's only limited 7 and not like 10, unlike this previous system, it can't represent this number. Now the clever part is, what did they do with this 2-digit number? Well, this 2-digit number is a number that tells the computer how many zeros you add after the number. So for example, if the 7 front numbers are these, like 1, 2, 3, 4, 5, 6, 7, if the 2-digit number is, say, 3, well, what the computer will do is it will take this original 7 digits and then add 3 zeros. Now, this still means that we still can't represent numbers like this. But in most cases, the logic is, if your number is already this big, you don't really care about the smaller numbers. You really only care about how big the number is in like probably the first few digits. So it doesn't matter if the smaller digits are not represented accurately because you're probably trying to represent a really big number. For example, since the number of back zeros is a 2-digit number, the size of the numbers that we represent become much, much larger. So for example, using the same example where our 7 front numbers are these 7, if our 2-digit back zero number is, say, 12, we can represent this, which is, I think, around 1 quintillion. And if we set this 2-digit number to like a negative number, we can also tell the computer to represent a decimal number instead. So for example, if we send it a -6, that's going to represent 0.000001234567 instead. So now, using the same amount of numbers that are possible, instead of just being limited to numbers 0 to 4 billion, we're now able to represent numbers up to really, really massive numbers with a lot of zeros, and also really, really small decimal numbers. Now, a peculiar thing happens when you're using this kind of system and you try to add a big number to a small number. So for example, let's take this number. This number is 1 billion. And we know that the number system can only represent the first 7 digits. So for example, if we take this number and try to add, let's say, 10, well, in the real world, and you add this to 10, what we'll get is 1, 2, 3, 4, 5, 6, 7, 0, 1, 0. Because we just added 10. But for the computer, we know that the computer can only represent up to 7 digits. So when we try to add 10 to it, the computer will think, okay, the target is 1, 2, 3, 4, 5, 6, 7, 0, 1, 0. That's not one of the valid numbers that I can represent. I can't do that. So what's the closest number that I can represent to that number? The answer is the same number. Because the number that you're adding is so small, the computer considers it as insignificant and it just throws it away. So same thing happens if you add like 100. So if you add 100 to this, it's 1, 2, 3, 4, 5, 6, 7, 1, 0, 0. The closest number that it can represent is still the same number, 1, 2, 3, 4, 5, 6, 7, 0, 0, 0. However, when you add something like 600, well, 1, 2, 3, 4, 5, 6, 7, 6, 0, 0, when the computer tries to find the closest number, it'll actually be 1, 2, 3, 4, 5, 6, 8. Because 1, 2, 3, 4, 5, 6, 8, 0, 0, 0 is only 400 away from the number that you want. Instead of this original number, which is going to be 600 away from the number that we want. So basically with this kind of system, the steps between each number that the system can represent becomes larger and larger the bigger your number is. So for example, here, it's already using 7 digits. The smallest step that you can add or subtract to this is 1. So this can go to 2, 3, 4, 5, 6, 7, or 5, 6, 8, 5, 6, 6, and so on. But it can't go down to like say 1, 2, 3, 4, 5, 6, 7.1 because it's already using 7 digits here. And yeah, when it has a 0.1, it tries to round to the closest number, which is the same thing. So here, the smallest step is 1. Or here, the smallest step is 1,000. And here, the smallest step is like, I think, 1 trillion. And here, the smallest step is like 0.0000000 and 1 here. So depending on how big or how small your number is, the smallest step that will change the actual value of the number becomes bigger or smaller. So the number system in GBG and most computers uses something similar to this. It's not exactly this, what I mentioned, like it's 7 front numbers and 2 digit for back zeros. It is something a bit more complicated. It uses numbers in base 2 and a few more special cases here and there. But the concept is basically the same. Basically has 2 numbers. One number is used for like precision, for like the small increments. And the second number is used for very large increments. And the specific number system that GBG uses is something called IEEE 754. So if you're curious about this topic and want to learn more, this is basically a standard across like pretty much every computer in existence. So you just Google IEEE 754 floating point and you can learn much more about that if you want to. Now let's go back to the main topic. How can we make use of this number system to do something useful? So in the IEEE 754 format, all the whole numbers that you can represent without skipping a number is from 0 to 16,777,216. So here in this map, I just use the large constant technique with this map to generate that number. So this is the biggest number that the number system can generate without skipping a number. And by the way, fun fact, the numbers that's shown in these like settings menu only goes up to like 7 digits. So you can see here it like gets rounded up to 20, but the actual value here is 16,777,216. So the number becomes so big that yeah, it's not being represented correctly. So if you're dealing with large numbers, keep that in mind. So let's see what happens when we try to add or subtract stuff to it. Let's say, let's subtract 1 to it. See here, 16,777,216 minus 1 becomes 16,777,215. As expected, and if we make this bigger, yeah, the math will check out. As I mentioned earlier, this is the largest number that the game can represent without skipping numbers. So what if I change this to 1? You can see here that 16,777,216 plus 1 is still 16,777,216. So this is the same as the example that I showed earlier. This number has reached the point that where it's so big that all of its quote-unquote front digits have already been used up, and adding small numbers like 1 is not enough to change the number. So when you try to add 1 to this, the value doesn't change anymore. It's still the same. And only when I make it move up enough, so if I change this to 2, only then will this change. So 16,777,216 plus 2 becomes 218 instead. So at this point, the minimum step is no longer 1, it's now 2. So you can see here, if I change this to 3, it now moves on to 20. So it skipped 219. And you can see that it won't be able to present any odd numbers anymore, since it only steps in 2s from this point. So if I try to increase it more, 4 is still 20, 5 still 20, then 6, it's going to become 22. Starting from this one, we can already see that weird stuff is happening when we try to add numbers. Now, what if we take an even bigger number? So let's take our original number here and then square it. It's going to become a even bigger number. So originally we have this number, and we square it, we have this really massive number. So what's this? It's 2.814e14. So if you see a number with an e plus a number, there's a simple way of meaning there's basically like 15 digits in this number, or have a really, really massive number. You still see it here. And if we try to like add, like say, 200 something to it, you can see that it's in 656, it's in 656, it doesn't change. So even like if I set this to like 1000, the number has become so big that even 1000 is not enough to change the value. So the minimum step at this point is already so big that you need to add a really big number to even change the values of this number. And this trend goes on and on. The bigger your number becomes. And actually, fun fact, the largest number that the IEEE 754 can represent is this. So it's basically 3.4 e to the 38. So it's basically a 39-digit number. That's the largest number that GBG can represent as well without going to infinity. And if you watch my infinity video, if you try to make a number any bigger than this, it's gonna become an infinity. So infinity is basically just a way of the number system telling you that, okay, this number, I can't represent it anymore. It's way bigger than the biggest number that I can generate. So I have no idea what this is. Here's an inf just to tell you that you've gone past the limit already. Okay, so how do we make use of these large numbers? Let's say we have a constant 30 going into this number object. So the input to the number object is 30. Here I have a map that has a really big number, so it's like 3e to the 10. So this is really big. So what will happen if we add this number to this input that has 30 on it? Well, based on our experience earlier, since this number is so big, and if you add like 30 plus that really big number, this number is so small that it doesn't affect the number at all. You can see here that from 32768 followed by a lot of zeros, even when we add a 30 to it, it doesn't change the value. Now, what would happen if we take this original number and make it negative? Well, we know that when we added this original number here, this number becomes the same as this. So when we add the negative version of this number, well, what will happen is the input to this number object becomes 0, and it will stay 0 regardless of what value we put here. Because regardless of any number that we set here, when it gets added to this really big number, the result is basically the same as this really big number. So it doesn't matter what this value is. And since we know that the value here after these two signals is basically this number, when we subtract it, it's going to become 0. So in this way, you're able to somehow turn off the signal entirely. Now, does that mean that if I add these two numbers to any input, it will always become 0? Well, let me show you another example. So here I have an example that's pretty similar. We have a constant. Those two maps, the same maps that generate the really big positive number and the inverse of that number. And we have these two number objects. These two number objects have all three signals connected to them. So the inputs to these two number objects are literally the same. However, when you look closely, this number object has a value of 0, and this number object has a value of 30. So what's going on? So here is the same as earlier. There's a 30. We added a really big number to make this a really big number, and added a inverse to become 0. But for here, what I did to do that was I'll add this really big number, give that, add this negative number, becomes that, then added this. So what this actually teaches us is that the order of when you connect connections actually matter. When you connect multiple connections to the same input, what actually happens is the game adds each of those connections one by one and not all at once. So here at the bottom, the order was we added 30, and then the big number and the negative number, which resulted in 0, because since this number came first, it was deleted by this really big number. But in this case, we added the really big number and canceled it out first before adding this 30 signal. And since after these two signals were combined, the number here was already 0, so it's no longer a really big number. And 0 plus 30, that's still 30. Doesn't matter what the previous number was. When the 30 came in, all it saw was, oh, the input here is 0, so it's going to become 30. So because of this floating point precision issue, adding is no longer commutative. And this reveals hidden mechanics of how connections actually work in the game. Now for this example, here at the bottom, recall, we added 30 first, then the big number, then the negative number. So now the number is 0. So what this means is, if we add another number, well, right now it's 0, so when I add 5, it's going to become 5. So here, there's even more possibilities that we can get given the same signals. If 30 was added last, then it's going to be 35. Or if 5 was added first, and then we added these two signals, so 0, and then it becomes 30. So that's another interesting thing that we can do here. Instead of just turning any number to 0, we can turn any number to any other number just by manipulating the order in which we connect connections. So with all this, how can we actually make use of this mechanic to aid us in our coding? Well, in this example, I just used constant values. That's just when you connect them, it's going to turn any signal to 0. But that really isn't helpful because when you start the game, it's just going to be always 0. So a way to make this useful is if we can somehow have the default state be just the normal value to it, and then find a way to activate certain neurons to send these two numbers to a specific input to turn it off, and possibly add any other number after. So let's try to do just that. Here we have a separate example. We have constant 30 going to the number object. So let's say we want to turn this into 0. Well, if we want to generate really big numbers, if you watch my map shaping video, you would know that we can use maps to make really, really large multiplications by using both multiplication and division. So here, let's just try that. So let's try to make the biggest multiplication that we can do with the map. So here, Since we want our signal to be activated by a button, the input is to start at 0. So we can like multiply it by 1000, but that's still not big enough to turn any signal 0, so I need to make it even bigger. So here we can try something like 0.12 zeros and 1. So here when we try pressing the A button, see that 1 becomes 1e to the 10. So that's basically like 10 billion. So at 0, the output is 0, and when the input is 1, when the button is pressed, the output is 10 billion. And 10 billion is big enough to turn this off. So let's see. Right now it's 30, and when we press the A button, it becomes 10 billion, and 30 just disappears. So now what we can do is just get another map, make the map generate the negative version of that. So make negative 10 billion. So you can just do this. And now this map will generate negative 10 billion. And so if we connect this map last, so recall the connection was this first, then this one and this one. Now we have a system where we can just press this button and the input of this turns into 0. And let's say if we want to change it to a different number, we can just add that signal after. So we can just do this, like say we want to turn it into 7. Any number that's in here, turn it to 7. We can just add this map after. So what happens is the original number is here, big number gets added, gets deleted, and then we add a 7. And there we go. Now keep in mind something I mentioned earlier, that the smallest step that a large number can take depends on how big a number is. So in this example, the largest multiplication that we can do with a map is up to 10 billion. So 10 billion is pretty big, but it's not that big. So if we recall earlier in our example with like 16 million, the largest step was like 2. So for this number 10 billion, I'll just tell you that the minimum step is now 1024. So what that means is if you add 500 to the number, it's just going to round back down. But if you add anything larger than, say, 512, if you add 600, 10 billion plus 600 is going to round up to 10 billion 1024. So we don't want that. Then we just showcase it here. Like 511, the exact threshold is 512, so 511. If we send the signal, it turns into 0. But if it's 512, what happens is, see here, the number becomes 1024. Because what actually happens here is, as I mentioned earlier, this is 10 billion. If we add 10 billion to 512, it actually goes up to 10 billion 1024. So 512 is big enough for the game to realize that, oh, the closest number that the game can represent is now 10 billion 1024 instead of 10 billion flat. And then when we subtract 10 billion from the number, that's why we result in 1024. So in this example, where we just have one map, the largest number that we can turn off is 511, or basically any number less than 512. So once you hit 512 or more, we won't be able to do that. Now, if that's a problem, well, what we can do is just send a even bigger number. Unfortunately, we can't do that with just 2 maps. We need to multiply it to an even bigger number first. That will cost an extra node on, but yeah, if you really need it, you can do something like that. See here, now with this extra multiplication, what does this become? This becomes 1e to the 70. So I have no idea how to call that number anymore. It's just a really big number. You see here that 512 now gets turned off properly. So if you need to turn off numbers bigger than 511, you need that extra node on. So this system is really useful in cases where you need to turn off a lot of different signals or change a lot of different signals. For example, let's have this example. Here I have 4 different textures that are turned on by 4 different things. And let's say we want there to be a condition where we want to turn all of them off at the same time. Well, if you're doing it with normal logic and normal coding, you would probably need to do something like this. Instead of just connecting the signals directly, you need to add like an AND and a knot and connect to the button so that when we press the button, the knot turns off and the end turns off and it turns off the textures. So with these 8 nodons, we can turn it off. But you can see here already, that's extremely costly. It's a lot of nodons. Like there's ways to shave this into 4 nodons instead of 8 nodons, but that's still a lot of nodons to just add the simple functionality of turning them off. Now with this new mechanic that we learned, we can do something like this instead. So instead of having to add all of these signals in the direct path towards the thing that we want to turn off, we can just have these two maps somewhere in our game, have a button or whatever condition that we want to activate it with, and just add these signals to whatever we want to turn off. And just with these 2 nodons, we can do that instead of using these 8 nodons. It becomes even more efficient the more signals that you need to turn off. You just to prove it to you here, when I open the game and press A, you can see that all of these textures are able to be turned off with just those 2 nodons instead of having to use this setup. So that's about it for this video. I hope you'll be able to make use of this new technique in your games, and see you in the next video.